Dr. R. Sugaraj Samuel. He is working as a professor in physics at New College, Chennai. He is also training students for IIT JEE, AIEEE and BIT SAT. He has more than 16 years experience in both teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals, which is prescribed for the syllabus for BSc Electronic Science by University of Madras. He has presented papers in several national and international conferences and has also conducted many training programs and workshops to motivate energetic students. His research areas are ultrasonic, polymers, crystal growth and photovoltaic systems. He is experienced in both regular classroom teaching and online teaching as well.
Welcome to UGC lecture series in electricity and magnetism. We have been discussing about the concepts related to electrostatics in this part of the lecture series. In today's lecture, we are going to learn a concept called electrical images. Before we start this lecture, let's see the session outline for today's lecture. In this lecture, we are going to learn about the definition of electrical images, the applications of electrical image pertaining to a point charge kept in front of a conducting earth plane and also a point charge kept in front of a conducting earth sphere. What are electrical images? From what do we call the charge as electrical image? The word image gives us a preliminary understanding that it is going to replace an actual one, an actual conducting sphere or conducting plate or any conducting surface. We are going to use an electrical image instead of a real electrified object. So, that is the main learning objective of today's lecture. We will see what is the definition we have for the term electrical image. Let us see the typical definition for electrical image. Electrical image may be defined as a point charge on one side of the surface which will produce on the other side of the surface the same electric field as is produced by the actual electrification of the surface. As I said, the electrical image will replace the electrified surface or electrified object or any electrified conductor or non-conductor, whatever it is. We are going to learn the concept with two examples also in this lecture. Let us see the concept of electrical image. There is one more point that we need to keep in mind, that is a very important point. What is it? The actual electrification of the surface is ignored and the image is used instead to find the field. So, this is an important point. Once we fix a point as electrical image of a particular electrified surface, after that we will totally ignore the surface and we will consider only the charge, which is called the electrical image of the particular surface, electrified surface. The electrified surface does not have anything to do with after we fix an electrical image of the surface. So, this is the concept of electrical image. The term is called electrical image because it is going to act as the real electrified surface as far as the calculations and formulations all are concerned. We will learn how to choose an image, an electrical image, maybe a point charge or even a collection of charges and all that. With one example, we will have more clarity when we take an example to understand the term electrical image. This is the typical example I would like to take up for getting the clarity. The concept of electrical image is well understood by the following earthed plate. See here we have a plate which is connected to earth. That means any charge that appears on this plate can be conducted to the earth. Earth is a large conductor which could take any amount of charge that is given to it, whether it is positive charge or negative charge, the earth will collect all the charges. So, that is the meaning of earthed conductor. This we have already learnt when we learnt about the induction process, electrostatic induction. Now, we have a point charge in front of it. See here we have a charge, it is at a distance d. Because this is connected to the earth, its potential is 0. So, that is marked as 0, V is equal to 0. For this arrangement, we have a positive charge here and an earthed conductor, a plate, infinite sheet. How do we replace this earthed conductor with an electrical image? How do we choose? I have taken the typical discussion on this side. We can replace the actual sheet which is connected to the earth. See, it has disappeared. This is only a line. It shows the position where the conductor was kept, the earth conductor was kept. Now, we have this as the electrical image of the conductor. It is not just randomly chosen as a negative charge. There is a concept behind that. It is the potential has to be 0 here on this because it is connected to the earth. Simultaneously refer to the actual diagram that is shown here. This is the original diagram and this is removed. If we want the potential to be 0 at every point on the line that we have represented, this is just a dotted line, it is not the conductor, it is just a line. The potential has to be 0 at every point. So, if we have a negative charge here, the potential will be 0 at every point, right, because the electrical potential is a vector quantity. If two charges having same magnitude and opposite charges at a particular distance, the potential will cancel each other. What is the potential produced by the positive charge will be cancelled by the negative charge, provided the distance is equal from the two charges, and that condition is met with in this case. Have a look at this. See, at every point I would like to just draw some lines and show you it is at equidistant, right. From the positive charge it is at a distance, from the negative charge also it is at a distance. If we take this distance as x, this distance is also x because it is at the symmetrical position. It is true for every point, true for every point. All the distances are equal from the positive charge and the negative charge. So, the potential cancel each other at the marked line. So, the typical condition is met with. So, we can forget about the charge, the earthed sheet, and instead we can have this negative charge which is represented as minus q here at the same distance d, the shortest distance d. Now, the negative charge minus q is called as the electrical image of the earthed infinite sheet. We need not have the sheet at all. Instead, we can have the negative charge. There are two things very important now. What should be the charge and at what distance it is to be considered from a particular position, maybe from the sheet itself, the original position of the sheet, or with reference to the positive charge it is at what distance. That does not matter, it is mere geometry. So, but there are two things we need to keep in mind. One is the magnitude of the charge and what position it is kept. So, these two will decide the condition, and this is called the electrical image. See, the potential is 0. This is due to the positive charge this term is due to the negative charge. So, they cancel each other and the potential is 0 at every point, not only the shortest distance. Now, having understood the electrical image with this typical example, we can go ahead with some calculations involved. If we have a long sheet which is connected to the earth and also a positive charge, finding the potential, finding the electric field due to the combination, all that will become very tedious. But if we replace the infinite sheet with one single charge, in the earlier case it was a negative charge at a distance d minus q at a distance d, the calculations also become easy because there are 2 point charges only, one is positive, other one is negative. We can do whatever we want, whether to find out the force between them, the electric field due to them and the potential due to them at any point, all the calculations become very easy. Shall we see how easy it is? We will take up the case and do that. Now, earth plane conductor which we have taken, we are going to do some calculations for it to find the electric field at a point P. See, this is the arrangement. What is the negative charge? Have you recognized what it is? This is the electrical image of the originally kept infinite sheet. I have just highlighted only the 2 charges here, the sheet is missing because it is not necessary, only the electrical image is now needed. We are interested in finding the electric field at this point. Consider a charge plus q placed at a distance d from the infinite conducting plane at 0 potential. Its electrical image is minus q at a distance d behind the plane. We can find out the electric field at the point P due to the positive charge, due to the negative charge which is the electrical image of the earthed infinite sheet. We have chosen a point on the axial line itself. We can take the 2 distances as x here because it is symmetrical, and this is the electric field due to the positive charge. This is the electric field due to the negative charge. Because the electric field is a vector, we have not included the sign of the charge q. We have considered the directions and we can resolve this into 2 components. All the calculations are already done. We are very familiar with the resolving of the vectors and then considering the resultant, all that. So, all calculations have been done, and here it is slightly modified way we are doing. We are just using the parallelogram law of addition. So, the same answer only we will be getting. See, this is how it is done. We have taken the parallelogram law to find out the resultant magnitude E1 and E2. E1 and E2 are equal in magnitude. So, we do the calculations at ease. We have already marked an angle theta for our reference. So, the calculations are self explanatory. We are able to find out the electric field. We want to replace the angle theta with the triangle that we consider. We can refer to the earlier diagram if we want. We have shown all the calculations here. This is the scalar form and this is a vector form. We have an n cap here. In the vector form of the expression for electric field E, the unit vector is perpendicular to the plane of the conductor. Thus, the electric field is directed outward and normal to the conducting surface. Though we have just marked an n cap here, we need to know what direction it is. I hope towards the end of this lecture, I would like to show you some pictures that will represent how the electric field would exist between the point charge, the original point charge plus q and the conducting the earth conducting surface at the visual. We will be able to have a visual about it. So, the calculation becomes very easy. We need not consider the distributed charges here that is appearing on the earth conductor. We have replaced it with the electrical image which is a point charge. What other calculations we can do? To find the charge density at P, let the induced negative charge on the conducting plane be distributed such that the surface density of the charge at P is sigma. By Gauss theorem, we know that the electric field at a point P is due to the surface is expressed in this way. This expression is very familiar to us, except for the minus sign. Why there is a minus sign? Because when we have a plane and we have a point charge in front of it, and the charge that is induced on this will be the negative charge. This side is connected to the earth. So, only the negative charge appears on the surface. So, surface alone is due to the negative charge that is existing on it. So, the charge density also should be given the minus sign. So, that is what is done here. So, we have a minus sign here. From this, if we want to rewrite the equation for sigma, and we can rewrite it like this, we know what is the equation for this E. Just now we have calculated. So, substitute that E here and we get the expression for the charge density that is appearing on the conducting surface, or else calculating the charge density is a very lengthy calculation. Just by the process of electrical image, the calculation becomes very simple. With the idea of little bit of geometry, we are able to arrive at easy expressions. Have a look at this expression. Here it is represented as R. The R is replaced with the distance d and x. X is the distance which we have already seen in the earlier diagrams. If you want to know what is d, what is x and what is r, you will have to go to the diagram and learn about them. So, finding the charge density becomes very easy. We can also find out what is the force of attraction that is existing between the plate and the positive charge that is kept in front, but we need to find out between the electrical image and the real point charge. Okay. Again it becomes the easy case of Coulombs law. Have a look at this. To find the force of attraction between the charge and the conducting plane. Why we are mentioning every time the conducting plane? For us the real object or the electrified surface is the plane, only the electrical image is the point charge. So, we should always keep in mind we are finding it between the surface and the positive point charge. These two are the real electrical objects. The negative charge which was represented in blue color in the earlier diagrams, that is an image, but for doing calculations we will consider the electrical image. This is how it is done. See, the force of attraction between the charge plus q and the induced charge which is minus q. What is the minus charge? It is the image on the plane is the same as that between the charge plus q and the image of the plane which is minus q, separated by a distance 2d. Now, this is the Coulombs law equation and that can be expanded. The bracket in the denominator is expanded and it is shown here. So, the force between the plane and the positive charge is calculated at ease, or else what we should do? We should depend on the integration, because the sheet has got the charge distributed on it. So, we need to find out a small region on the sheet and then integrate it over the entire surface. See how tedious the calculation would be, but here the electrical image is a point charge. So, between the image which is a point charge and also the positive charge which is already a positive point charge, we are easily finding the force. So, this is an easy concept, so that we can replace the electrified surface with a point charge. We have done it for a plane surface which is connected to the earth. Is it possible to construct or to consider an electrical image for a spherical charge? Because we move ahead with a 3-dimensional object and all, no. So, we will take up an electrical object which is in the form of a sphere which is also connected to the earth, and how to find out an electrical image for it. We will go ahead with the discussion. This again shows the electric field can be found out at any point at ease, the point charges are only considered. Now, we will go ahead with the conducting sphere. Let a point charge plus q be placed in front of an earth conducting sphere of radius r. We can try to replace the conducting sphere by considering a suitable electrical image for the sphere. So, this is the arrangement. We have a positive charge here which is plus q, and this is the sphere, this has radius r, which is connected to the earth. What will happen again by considering the induction? We have a positive charge here, so negative charges will be coming closer to this, and this side the positive charge is connected to the earth. So, once we replace it, no, it will have full of negative charge. All the concepts are known to us, so I do not want to explain it again. This is the arrangement: an electrified sphere which is connected to the earth, and in front we have a positive point charge plus q. Maybe the distance could be taken as d, and then we will go ahead with the calculation. We need to find out an electrical image for this sphere. Let us go ahead with the discussion. To find the magnitude and location of the image charge, what do? Let the charge plus q be placed at a distance d from the center of the sphere of radius r, which is earthed. We need to replace the sphere by considering a suitable image charge, so that the image along with the plus q makes potential 0 at any point considered on the surface of the sphere. Let us choose a point P on the sphere, and we need to prove the potential at that point is 0 by considering a suitable image charge for the earth conducting sphere. Here we have a clue. What is a clue? The sphere is connected to the earth, its potential is 0 on the surface. At all points on the surface the potential is 0, that is the clue. So, we need to consider an image that also produces the potential 0 at all points on the sphere. And moreover, what about the magnitude? Based on the plus q, we need to find out the sign of the image charge and also its magnitude, right. All that we will be able to do with one clue or one important or vital point, that is the potential at all points on the surface should be 0. That is the clue for us. Let us go ahead with the formulation. Let us choose a point B on the line joining the center of the sphere and the point charge. So, that see, this is the point B, and we would like to fix a charge q dash at this point. On what basis we are choosing it here? Because the entire sphere has to be replaced by this q dash. We need to find out the magnitude and also the charge. We have some geometry concepts here. This distance OA, which is the distance d, and OB is this distance, is equal to r square. It is based on the triangular law, right, and also this is a main reason for this. Hence, the triangle OAP and OBP are similar. We are able to write all these expressions. These are self explanatory, I do not want to indulge further into this. This is by geometry. The ratio PB divided by AP is constant whatever be the position of the point on the sphere. Where is BP? So, this is BP and AP, this is the distance AP. As far as this arrangement is concerned, for all the points this ratio will be true. What I have shown here, the BP, I would like to highlight, this is a key point. Based on this ratio, which is constant for all the points because of the geometrical arrangement, we are going to take the derivation forward. How it is done? See here, let the charge q dash at the point B, then the potential at P is calculated because it is a scalar thing. So, from the point Q, point charge Q, and from the point charge Q dash, we have taken the distances and the potential at the point is considered, and we do the simplification based on the geometry, and we have this condition which is a vital condition which I have been telling again and again. The potential at all points on the sphere has to be 0. So, the Vp has to be equated to 0, the potential at the point P. So, based on this we are able to finally arrive at the expression for q dash, and automatically we are having a negative sign for this. So, the q dash has to be negative in sign. And what about the magnitude? In comparison with q, the r divided by d, this is the ratio we have. So, based on this we need to have the value of q dash. What about this r divided by d? R is the radius, d is the distance between the center of the sphere and the point where we have the positive charge. And the distance OB is also now given in terms of the r and d. See, this highlighted expression is for the charge q dash, and this highlighted expression is for the position OB. So, by considering the geometry and also the vital condition, the potential at all points on the surface of the sphere should be 0, we are able to easily arrive at the value for q dash and also the position. So, the magnitude and sign of the charge and also where it is to be placed, both are calculated at ease. Now, the entire sphere need not be considered. Its image, which is marked as q dash here, which is at the position B, this too will do. This is the real charge A, and the sphere is replaced, the point charge, these two will take the lead role in finding out the different quantities like electric field and potential at any point. Suppose we want to find out the potential at this point P, yeah, it is easily done with the geometrical arrangement. So, we can substitute for PA and PB based on the geometry. I do not want to explain about the geometrical aspects because it is to be visualized in the image, and accordingly we have to substitute the values. What about the expression for potential? See, the potential is shown here, and similarly the electric field, but here I would like to highlight one point. The electric field is calculated by considering the radial component and the angular component, and we use this polar representation for finding out the electric field, because electric field is a vector, accordingly we do the calculations. In the earlier lectures we have made an attempt to find out the electric field due to two different charges at a particular random position, maybe for a dipole, right. The same way here also, but for two different magnitudes we are able to find out the electric field at ease, right. So, that is how the calculations are simplified. Now, once again, how do we find out the charge density on the surface? The same concept as I have explained earlier, we are doing it. The electric field is known, so we substitute it here. And similarly, the force between the sphere and the point charge plus q, right, is to be found out for the actual charge q and the image charge. So, once again it is done at ease. Now, what about the electric field, how it would appear, which I have already promised you, right, how the electric field would exist. In the case of a sheet, we had an end cap that represents the direction of the electric field. Because we have learnt the two cases like earthed sheet and also the earthed sphere, we can have a look at the electric field for both of them in this diagram. See here, we have a positive charge, this is a sheet which has been replaced by this negative charge. The electric field exists, as I have said, at every point on the surface. The electric field is normal. See, it is normal at this point, it is normal at this point, normal at this point. Not only for this plane sheet, even for a sphere, the induced negative charges are appearing here, and at every point on the surface the electric field is normal. It is ending at the negative charge, but it is normal at the surface. So, how beautifully we are able to use the concept of electrical image to replace the electrical surfaces. Hope you have understood the electrical image with these two examples. I think it is a time for us to summarize what we have learned in this lecture. Shall we look at the summary? In this session, we have seen the concept of electrical images and the applications of electrical images pertaining to a point charge kept in front of a conducting earthed plane and the point charge kept in front of a conducting earthed sphere. Before we wind up this lecture, let us test our understanding by answering these questions. Explain the concept of electrical image with suitable example. Discuss in detail the concept of electrical images for a positive charge kept in front of an earthed infinite conducting plane. Discuss the concept of electrical image for a point charge kept in front of an earthed conducting sphere. So, with this I would like to wind up today's lecture and see you in other lectures with other concepts related to the electrostatics concept. Thank you for watching this lecture.